Hi, today I'm going to talk about what type of experimental testing you need to do if you want to calibrate a temperature-dependent material model for a material. In the past, I've developed test plans that I've presented in different videos for how to test a rubber, a thermoplastic, or a thermoset, different types of polymer studies, for material model calibration. And as part of these test programs, I've been focusing on a single temperature. And then I have said, repeat the testing at multiple temperatures if needed. And that's kind of the blanket statement I've been giving. But the question that I got was, well, what does that mean? Do I need to really repeat all the experiments for all temperatures, or are there cases when that's not necessary? And that's what I want to talk about in this short video. So to answer this, it's important to start thinking about why are we doing experimental testing. The goal here in our minds is we want to come up with enough experimental data that we can calibrate a temperature-dependent material model for use in a finite element program. And as I talked about earlier, there are really two ways to do this. One type of material model is based on linearly interpolating the parameters based on the temperature. And the other way to do it is to use a material model and a set of equations that directly depend on the temperature themselves. So these are two common ways to do it. And it turns out that the most common of these two is the case where you actually calibrate a material model for each temperature, and then you have the finite element program interpolate the individual parameters for intermediate temperatures. So in essence, you need to calibrate the material model for each temperature, and since that's the requirement, you actually have to do all the experiments at all temperatures. Otherwise, you can't really find the individual temperature-dependent material models. So that's the story. If you have a material model that you want to use that needs to be interpolated, the individual parameters, do all the experiments at all temperatures, and it gives you a lot of freedom, it gives you a lot of accuracy, but it also requires a lot of tests. The other approach, which is very nice when it works, is to use a set of equations that describe the temperature dependence. And most material models in your finite element programs are not in the form where the equations actually depend directly on temperature. There are some examples of when this is the case, for example, linear viscoelasticity, or with TTS, time temperature superposition, that has a very specific temperature dependent type equation in it. So that's one example where that works. Another set of equations where this is applicable is, for example, in the PolyUmod library of user material models from our company, Polymer FEM. Here's an example at the bottom that shows you a very specific equation for how the modulus changes with temperature. This is available in the TNV model, for example, in the PolyUmod library. And if this is the equations you want to use to describe material as a function of temperature, you need to find the parameters in this equation. And one way to do that is to run a DMA temperature sweep that measures the modulus as a function of temperature. And from that, you can directly find these parameters. So that's a very specific additional test you would need to run to find these parameters. Another example is the PolyUmod TNM model, the three-network model. The three-network model is a viscoplastic material model too, and it has very specific equations for temperature dependence that work in a somewhat narrow range of temperatures. And it basically says here, the first equation is the stress for network A in this model. Is the shear modulus depends on temperature here. Theta is the actual temperature. Theta 0 is a reference temperature that you can pick based on the experimental data. And theta hat is the parameter that you would need to find. And there are three networks in the three-network model, obviously. So you need to find this for all of these networks. Similarly, the temperature dependence of the viscoplastic flow of the three-network model has this equation here, where you have n, the lowercase n is the power exponent that controls how the yield stress depends on the temperature. What's cool about this is that they're very simple equations, and that has the benefit that you can actually find these numbers, these parameters, for your specific material using a single experiment that was performed at a different temperature than the main set of equations for the calibration. So in this case, you do full testing at one temperature, and perhaps just one or perhaps two test at other temperatures to find these additional equation-based parameters. So that's a TNM mol, and it's mol specific, obviously. To summarize, in most cases, if you want to calibrate a temperature-dependent material mol for use in finite element simulations, you are unfortunately forced to run all experiments at all temperatures in order to create an individual material mol for all these temperatures. Remember, when you calibrate your material mol in the end, it's good to calibrate the material mols one at a time and do it in order of temperatures. So when you do the second calibration at another temperature than the first, your starting point in the calibration should probably be the answer at the previous temperature, because you do want the parameters to vary as little as possible from one temperature to another. And then the exception here is if you use an equation-based material mol, like the PolyU mol, the tree network mol, or the TNV mol, then you can get away with less experiments at other temperatures because the equations control that, and you just need to find the individual parameters in these temperature-dependent equations. So that's how I would think about this when you test your material. Think ahead of what material mol you want to use, and that will guide you in terms of what type of experiments are needed. If you have any questions on this, you can ask them below.